Okay, chat window is open. Participants window. So, okay, email. Okay, can see my screen, right? Okay, so we are looking at first page. Okay, first page, first question, quite straightforward. Anyone needs me to go through? 22. If yes, you just type yes inside the chat. Oh, yes, okay. For one, look. All right, so this one here, right? We have three resistors there. Then they give us some configurations for the switches, switches A and B, whether they're open or closed. So there are four possible outcomes, and then they tell you they measure the resistance for you, lah. So remember, you're measuring resistance between these 2 points, this point and this point, X and Y. Right, so you're looking for the pathway. Right, so I don't know how many can hurt. That's right. Okay, so first one, both switches are open. Okay, both switches are open, right? Then we trace the path. The only path that can happen is like that, like this. This is the only path you have, like that. Okay, so this one you have to go through all three resistors lah, right? And you get a 24. So let's write this outcome here. So this is basically saying that, oh, R1 plus R2 plus R3 is equals to 24 kilo ohms, right? Okay, then this is the first one. Okay, second one, can I go erase out this line? Erase out this line. Okay, second one, A is open, B is closed. Okay, so B is closed. Let's close out B. Close B is big. Okay, let's see what paths you can take right now. So again, we trace. Okay, you can go from here. Okay, you cannot come down here because this is black. This open, right? So it goes like this, then come to here. At this point, right, it has two possible paths. You can either go down or I read the person. Okay. Okay, so you can either go down or come up. So these are the two possible paths here. But look at the two paths here, right? The bottom path, this is a short circuit. Okay, so a short circuit provides the way for the current to go past, to bypass the resistor lah. That means the only path you have here, right, is like this. Okay, it goes like that, down, up, to B, and back to here, and back to here. Okay, so you bypass resistor R3. So now you get R1 plus R2 is equal to 20 ohms. So you write R1 plus R2 is equals to 20. That means, right, my R3 is equals to 24 minus 20. I get 4 kilo ohm. Okay, so this is it, right? 4 kilo ohm. Okay, let's look at the next one. Next one will be A closed, B open. Okay, so let's change this out again. Okay, we close A. Let's use a factor marker for this. Okay, close A. All right, close A. Okay, then the path becomes, okay, so again, we look for chances where you can short circuit. So you come to here, again now you can either go this way or you can come down this way. So this path here is a short circuit. Okay, so when you can short circuit, right, the current will go through there because this is a path of least resistance. So that means right now you have to just go through R1, then come down to A. Oh, sorry. Go through R1, come down to A, then back to Y. Okay, so you bypass everything. Okay, it's just R1 lah. So from here you can write R1 is equals to 12 ohms. Okay, that's right. Okay, R1 is equals to 12 ohms. Okay, then the last one, both switches are closed. Let's just check what's happening. If I close both switches, okay, I close both of them like this and like this, right? Then you are still just passing through this, this, this. You don't have to care about the rest of it. So this is still just R1. So this is, okay, right here. So this is R1 plus R2 plus R3. This is R1 plus R2. This is just R1. This is just R1. Okay, so R2 is equals to, so R2 must be equals to 20 minus 12 lor. So you have 8. Okay, so you're supposed to find R1 over R3. R1 over R3 is 12 over 4. So we have 3. Okay, so that's question 22. Okay, okay, moving on. Okay, 23. 23 is a very interesting question, so I'll go through it. Okay, okay, 23, let's look at the setup first. Okay, this one I was trying to think of how to explain it last night, but it's not so okay. I get what's happening, but to explain it was not so easy lah. Okay, you have a sheet of conducting paper of aluminum of uniform thickness. Sorry, cut to the shape. Okay, so this paper is conducting. All right, so this paper here, this one over here, all right, conducting, then connected by aluminum strips, all right? Then high resistance voltmeter is connected as shown. So this is the voltmeter over here. Okay, so you can see that this is a path. There's only one path for the current to go. The current will go like that. Okay, like this. Okay, current doesn't go through the voltmeter because this has very high resistance. Okay, which is what you want. You don't want any of the current to be diverted out of your circuit. Your main circuit is just this fellow here. Okay, so now you're asked to, then you basically take this lead, right? You put it at different positions, right? Then go and read the voltmeter reading now. Okay, so if you then asked to draw a graph of voltmeter reading versus distance, okay, let's just do the basic one first. Let's say instead of using a strip like this, right? I use a strip that is like that. Okay, uniform strip. Okay, I go this way. Okay, then you should be able to see that if I take my probe here, right? The voltmeter is here, right? This length, okay, this L, right? Okay, let's say this L. This whole thing is, let's say, capital L, right? And this is E, right? I can say that, oh, sorry, V equals to small l over capital L times E. Okay, so this is a standard one. Okay, this is basically your potential meter lah. All right, but this guy here is a bit different. This guy here, right? The resistance is actually decreasing. Okay, how do you know that? Because the paper has uniform thickness. Okay, so that means if you draw the cross section, right, the paper looks like this. Okay, if it's uniform thickness, it looks like this. All right. Okay, but because now this guy is fatter here, right? Okay, I expect my cross section area to be here. This cross section area, this you take a cross section here. This A1 versus A1 versus A2, right? I can say that A2 is larger than A1. Okay, going by this, if I identify a thin strip here, say I just draw this thin strip here, like that. This thin strip here and versus this thin strip here, right? I can say that this R2 is smaller than R1 because I know that R is equals to rho L over A. Okay, the smaller the cross-section area of your conductor, right? The larger the smaller the larger the cross-section area, the smaller the resistance. Okay, so how does this circuit work? Okay, so let's say if I need more space about time. Okay, so if I give you a circuit with let's say I give you even resistance, right? So all of them have the same resistance. Okay, then this is R. Okay, then connect them up. Okay, take one cell like this. Let's say this is E, right? If I connect them up, if I take a voltmeter reading here, okay, so if I take a voltmeter, I put across here, right? This one will be E over 5. If I put like this, E over 5, E over 5, E over 5. If I put like this, 2E over 5. Okay, if I put like this, it will be 3E over 5. This is a proportional increase. Okay, so far, okay? Any questions up to this stage? I pause for a while. So you need to understand this one first. Okay, how to have. So now the cell is a bit different because I can see that as I go down this path here, right? This portion here, okay, this portion here, the resistance is constant. Okay, every stretch increases by the same amount. Okay, then once you come to here, this widens out, right? This widens out, right? So as it widens out, the area becomes larger, right? Area becomes larger here. So that means for the same increase in distance here, right? The increase in resistance is actually falling. The rate of increase is actually falling. Okay, so if I were to draw my resistors here, right, they basically look something like this. You have a very big resistance at start, okay, and then you have a smaller resistance, then have an even smaller resistance. Okay, so you tap. Okay, tap. Okay, like this. Circuit here. Okay. So this is R1, 2, and 3 lah. So I can say, oh, R1 is larger than R2 is larger than R3. Okay. So now when I tap, right? When I tap the voltmeter across here, it's a voltmeter. If I tap here, okay, if I tap like this, hold on, if I tap like this, right, I get a certain potential difference. When I tap the next one, today very popular, more people coming. Okay, when I tap the next one like this, right, I will get an increase in the potential difference, but the increase is not going to be proportional to the first one. Okay, so what I'm saying is if this one gives you a reading of V1, this one will not give you a reading of 2V1. This will not give you a reading of 3V1. Okay, the increase is not proportional here lah. Okay, so the best answer for this one here is D. Okay, why D and not B? Okay, B, right? Okay, B, yes, sure, there's also increase in voltmeter reading, and there's also this increase here, right? You actually want, yeah, but here, right, the main issue is with the portion in black. This portion here. This portion here, right, you are still increasing your horizontal distance. When you increase your horizontal distance, right, that means you're tapping, let's say, at first you tap like that. Then now you tap somewhere here. This increase in distance, right, should increase your potential difference reading. Okay? So that's why as you go, right, this will increase. So for this portion here, every delta X will increase by, right, your total resistance will increase by a fixed amount. That means your PD will also increase by a fixed amount. But when you come to here, this portion widens out, right? Every strip will cause a smaller than previous increase. Okay, so your curve will kind of flatten out this way, this portion here. So this is the portion where it flattens out. Okay, then once you come to here, this portion here, right? This portion, again, this is a uniform increase, but now the increase is smaller. It's compared to this guy here, this is smaller already. Okay, so over here, your curve will be not so steep compared to this initial portion. Okay, so this is a quite a good question. Challenging, I agree. This one. Questions you can type. This one I think you might need some time to process. Uh, okay, can. Any issues for this one? Don't have, huh? Go on. Next one. Okay, next one. Actually, this one is quite not too difficult, I think. Yeah, so this one is quite straightforward. This one you just need to write out. Okay, so you have n turns of cable. Okay, this one a lot of terms to highlight. So just like COE contains n turns of insulated copper wire wound on a cylindrical iron core of diameter D. Okay, copper wire has a diameter D. Resistivity is rho. Diameter D, capital D is much larger than small diameter D. So you have a cable. This cable is, I don't know how to draw the cable, but the cable goes like that, right? This cable here, right? If you draw this cable has a diameter of D. Okay, and then you take a coil, you take like a toilet roll, right? Okay, like this, right? Like that. So this guy has a diameter of capital D. You take this wire coil around it, and you have two leads. That's what I'm doing. Okay, so this one you want to work out total resistance, right? So total resistance, right? You need R equals to rho L over A. Okay, L here, right, is the length, the total length of the wire. So you need to find the number of turns multiplied by the diameter of the coil. Times the circumference of the core lah. So this one become rho. So you have I times D. Okay, this is the circumference of core. Okay, divided by A. A here is a cross-sectional area of cable, right? Oh wait, there's an n term, because you need to multiply by n to give you the number of coils. Okay, then bottom is just pi d squared over 4. Okay, you rearrange this guy, you will get 4 rho n d over d squared. Okay, so this one, no problem. 4 rho n d, so answer is A. Yeah, anything just voice out loud. Okay, next one. So quite interesting question. Okay, next one, this is your potential divider. So you have four different resistors, P, Q, R, S, okay, connected to a battery. Voltmeter reading is 0. Okay, so voltmeter reading, remember a voltmeter measures the difference in the potential. So this is A and this is B, right? So you read VAB, right? You are reading the potential of A compared to ground minus the wave potential of B. Then you're finding the difference in the slope in that sense, lah, right? So you just imagine that, oh, you have one slope that is going down like that, straight down. Another slope that's going down maybe like this. Okay, you want to find the difference in height. Okay, so what you're doing is that you have this height here, at this point here, right? What is this height? H1 versus what is this height? H2. You're comparing that when you talk about potential difference. Okay, so basically, what you know is this. Okay, so let's say this is E. This EMF is E, right? Okay. I know that basically, right, okay, let's mark up this point. Let's call this point okay, let's call this point C and call this point E. Okay. So I know that VCD is just equals to my EMF. Okay. But because VAB, okay, because VAB is equals to 0, right? That means my VCA minus VCB is also equals to 0. That means VCA must be equals to VCB. Okay, that means the potential drop must be the same. So what I'm saying is that if this guy, okay, maybe just take this, okay. If this guy drop by, I won't have the numbers. Let's just take a number here, okay? Okay, let's say this is 10 volts. Okay, 10 volts. Let's say that, okay. If across P drop by 5, this guy also must drop by 5. If this one drop by 3, this one also must drop by 3. So it's an equal drop in that sense. Okay, so once we have that, right, we can form the relationship in terms of the potential divider lah. Okay, let's try to find VP. Okay, VCA, right, is equals to VP. VP, right, is just resistor of P over resistor of P plus Q times EMF. Okay, then to find VCB, which is just VR, right? VR is R over R plus S times EMF. Okay, and because these two are equal, right? I can say that P over P plus Q is equals to R over R plus S. Okay, from here, I can actually I can just simplify the whole thing. I think I'm overcomplicating this guy. Wait. Let me just erase this fellow here. Okay, so if for example, okay, just give you some numbers. Let's say this is 2. Okay, let's say this is 2 and 3, right? And this one must be 4 and 6, for example. Okay, they have the same ratio. So I can say that P over Q is equals to R over S. Okay, for them to have the same ratio lah, to have the same drop. Okay, same drop in potential. So if I cross multiply this one, ES equals to QR. Okay, so answer is D. Okay, so they have to maintain the same ratio in order for them to have the same drop. Okay, remember this potential divider goes by your proportion of your resistance. So you want to know what is the proportion of this resistance to this whole resistance. Okay, but that's why I just wrote P over P plus Q lah. But actually I realized it's just comparing P over Q that would do as well. Okay, pause for a while. Okay. And I move on to 20 now. The potential meter one. I don't get the relationship. Actually, I don't know whether I can derive it properly. Let's try. Not just now, my problem was I don't think I solved the equation. Let's try to find some space to squeeze this in. Okay. Tobias is asking, so Tobias, if I write it this way, right? If I write it as P or P over P plus Q times EMF is equals to R over R plus S times EMF. Is this okay for you? Do you understand why it's equal? Yes, okay. So how do we solve from here? This is the problem now. Uh, I don't know. Let's try and see. If I cross multiply them, okay, I think that's the next stage we need to do, right? So we have PR plus PS equals to PR plus QR. Then the PR can cancel. And PS equals to QR lor. Okay, right? Yeah. I also didn't see the other way. The moment I see this two, I scared. I don't want to do it. So I come back to the lazy way and skip step. Okay. In short, don't be lazy. Okay, 20. Okay, 20. Okay, so you see this package I put together is basically just nice. They have a good spread of questions. I think this one was from JC2. I think it's NYJC. Yeah. Okay. Okay, so let's look at this one here. Okay, I have a potential meter circuit used to determine the inter-resistant R of a cell, EMF E. Driver cell has an EMF of 2 volts, negligible internal resistance. So highlight this stuff. Internal resistance, EMF E, and R. So this is the bottom circuit, E and R, right? Then you have 2 volt driver cell over here. Internal resistance negligible. Resistance wire PQ is 1 meter long. Okay, then this cell is connected in parallel with a resistor of 2 ohms. So 2 ohms is here. Okay, then switch S is over here, right? Switch S open, balance S 0.50 meters. Okay, let's see. All right. Okay, so when you open the circuit here like this, right? Okay, so let's say you open now, you are just comparing this portion. You're comparing this like that. Okay, you are not considering this. Okay, so remember your galvanometer measures current. So it's about whether okay, no matter how small current, it's not got current flow through, right? You will read already. So this comparison here, so let's say this length here, this is let's call this VP. Let's just call this point R lor. Okay, so VPR. Maybe should be R, because R is a letter for resistors. Let's call it VPA at this point here. So if you write down, okay, so when I have balance of centimeters, right? So when L is equal to 0.70 meters, my VPA I can calculate. So this is just 0.70 divided by 1.00 times 2 volts. Okay, so I get 1.4 volts. Okay, then I just redraw this circuit. This is basically like this. You can treat this guy as This is VPA. This is 1.4 volts. Okay, this is connected to your unknown EMF of R, E, and then internal resistance of R, small r, and then your galvanometer is here. Galvanometer is here, like that. Okay, so in order to have balance, right? That means, okay, when balance, okay, my VPA is equals to E. That means my E is equals to 1.4 volts. Okay, so this is the first part. Okay, so second part, let's do the second balance. And second balance is quite B lah. Let's B here, B here. Okay, so then now we continue. When S is close, okay, my balance line become PB. So VPB is equals to 0.5 over 1.0 times times 2.0. So I get 1.0 volts. Okay. So now your circuit is when it's close, this close, right? You are once you close this guy, right? You are actually measuring the terminal voltage across this cell. Okay. So this connection is the same as you holding a voltmeter across here. It's the same connection. Alright. So you're reading the terminal voltage across the cell. So when you're doing that, right, you want to find the terminal voltage, right? Okay. So you can say, oh, VT. Okay, VT. That's right. So let's write terminal voltage across cell is equals to VT. VT is equals to 2.0 over 2.0 plus R times E. Okay. And then because it's balanced, right? Okay, because it's balanced, I can say that VT is equals to VPB. So once I have this is 1.0 equals to 2.0 over 2.0 plus R times 1.4 volts. Okay, then go and solve for R. Okay. If you're not sure, please ask. Yeah. Since you're here, might as well ask. Save you booking a consultation. Because I know a lot of you don't want to come consult, so I create this session.
Mr. Fang, I don't
Yeah.
get how the voltage across PB is the same as the voltage across the 2 ohm resistance.
Oh, when the switch is closed, is it?
Yeah,
Yeah, because you want it to be balanced, ma?
but
So wait,
I
so
don't,
okay, if
I
you
don't
were
get
to
what's balance.
yeah, so you redraw the circuit, right? Hold on, I just redraw it here on top. Okay, so you want the okay, so basically you have VPB on top, right? This is VPB. Okay, then your circuit becomes like this. Oh, oops. Comes like that. Like this, right? Okay. If I were to draw it differently, if I give you this is a color to draw. If I give you this E R 2.0, then I take a voltmeter. Hold on. I take a voltmeter, I connect like that. Will you be able to calculate the reading of the
Yeah,
voltmeter? Can, right? So basically
yeah.
you take, yeah, you know let's say you know small r, right? And you know small r and capital E, you can work out the voltmeter reading, right?
Also, the PB becomes like a voltmeter.
Correct.
Okay, okay.
So
Okay, I get
yeah,
it.
so I think Raju raised a good point. This guy here, right? This wire here is basically serving like a voltmeter. Okay, so remember when we talk about voltmeter is supposed to have infinite resistance, right? But in most cases, it's not lah. There's nothing as infinite resistance. So what happens is that this one here, right? We realize that this setup here, right? It doesn't care whether your cell here has internal resistance or not. Because yes, you might have internal resistance, right? But as long as your this potential difference and this potential difference is not equal, right? No matter how small the difference and how big this R is, right? You will still get some reading on your galvanometer. Okay, as long as this difference is non-zero, okay, you will not get zero for here. If you not get zero for here, that means that you will be able to detect any small current. The moment you detect a small current here, right? That means VPA is not the same as E. That means you have not balanced it. That means you need to adjust VPA over here until you get your galvanometer reading to be zero lah. So this guy is working like a voltmeter there. Yeah, so potential meter is quite take some time to go and try the questions. You flip through a TOS, there should be a lot of questions on galvanometer lor, or potential meter lah. Just dig a bit. If you want, I can go and dig I got very old TOS I can go through lor. Okay. 20, yeah. Okay, this one. Okay, this one is an interesting setup. Okay. Basically, you have different paths to go lah. One, come out from battery, go through milliammeter, go through RF, go through one of the resistors. Let's say now this one's going through here, right? Like that. This is one really. Second one, you do like that lah. So you're tapping through individual resistors in parallel lah. So this is how you vary your experiment lah. Okay, so you can make 1, 2, 3, 4, 5 readings. Okay, so then I give you this graph. This graph of R versus 1 over I. And it's also clear what this is about. But here, right, the only equation you can form is you can form in terms of your total resistance, current, and EMF. Okay, so we know that current is equals to EMF divided by, let's use a nice the original E, is it right? E over total resistance here. Okay, so for any path, the total resistance is this now. So I equals to E. Okay, total resistance here is R plus RF plus whatever variable R you give it. Like that. Okay, then you cross multiply them. Okay, because small r and RF are both constants, so I'm gonna group them together. Okay, so you cross multiply this guy, right? I get I times R plus RF. Okay, this is a constant here, right? Okay, plus IR, and this is equals to E. Okay, that's how I rearrange the equation now. So I want to form into this state. So you make R the subject. Okay, so I rearrange this guy. Okay, I will divide everything by I. Okay, if I divide everything by I, right? Okay, so let's write down the point. Then making R subject and dividing throughout by I. Okay, I get this. Okay, so I get R equals to E over I plus minus, sorry, minus R plus RF. Okay, then continue. So I get R equals to E 1 over I. 1 over I minus R plus RF. Okay, so now our equation is formed. So this is my Y, this is my M, this is my X, this is my C. Okay, so then you can fill in the blanks. Okay, so this one here, this is gradient is EMF. This is negative R plus RF. Okay, so it's the math part lah. Okay, not too difficult. You just need to, I think it's a bit confusing because you might not know how to start. So go back to the basics. So you start from basics, you can't really go wrong. I think yeah, there's no shortcut for this question. And okay, 4A okay. Okay, 4B I skip. 4B 24 thin strands of cable. Right? Just know that this is in parallel. Parallel. Okay. So basically this is 24 cables in parallel. We work out RS first. Strand. That's right, it's full. Oh, where's not okay. R strand is equals to rho L over A, right? Then R cable is equals to 24 over R strand. R strand over 24. Okay, so this one don't need to do so much. Okay, this one, explanation. I think someone here asked me this before. Was it Tobias? No. H1 to ask me. Okay, so this one, be sure you know how to explain. Don't screw this up. This one, quite straightforward. Don't cock it up, okay? Okay, so this one, this is question. I go to the solution straight now. Okay, so be sure to hit the points. All right, so you want to always talk about this one. This is important. So this is the main thing. Okay, amplitude of vibrational matter. Do not accept matter, atoms, molecules and particles. So they want you to use the key terms here. Lah. Anyway, this is based on other schools, on which but I agree with this one to be clear about the terms. Okay. So drift velocity decreases. Okay. So basically your electrons are being impeded by the increased vibration of the lattice ions. Alright, so 3 points. Okay. So first one, let's write out this one over here. Yeah, I write on the other side. Lah. The one that I shared later. Okay, so let's do this. So as temp increases, vibration of lattice or metal ions increases. Okay, so that's one. Hence, impeding movement of charge areas, reducing drift velocity. Okay, this resistance equals to PD over I, right? Current decrease means resistance is reducing drift velocity and hence reducing current. Okay, so you know that the terms here, right, you have to be very careful. So the old syllabus a few years before you guys, right, they never talk about drift velocity. So this is a new thing. So when you talk about your lattice ion structure, how it impedes your electrons, right, you definitely, when you talk about current now, you have to think about it from the drift velocity point of view. So this is your I, oops, sorry. Your I equals to NAVQ equation. Okay, you're talking about this term here. Okay, so make sure you hit the points for this. Okay, so this kind of marks, exponential marks, please go and if you cannot fully understand, if you need to memorize a bit here and there, please go and do so. Okay, but again, I said this is not too difficult to do. Okay, moving on. Okay, two. Okay, usually for circuit question, right, there's a bit of, okay, not say problem solving per se, but there's more logic involved than anything else. You basically you try to establish the across each of them, right? Across each of the resistor, right? What are the values that you use in terms of current and resistance and all. Okay. So for this, let's make some consideration first. Okay, so we start off. Okay, we have a 10 volt resistor here. You have R1A and R2 and B, right? Okay, so let's establish some facts first. Okay, I'm going to write down some uh, letters as well. Okay, so I'm going to mark this point as point C, and this point is point D, and maybe this is, I don't really have this point E and point F. Okay, I shouldn't use F because I should use E because E is EMF, right? So let's call this point F and call this point G. Okay? Okay, so let's establish some facts first. I know that there will be a current coming out, obviously. So I1 will go through R1 and I1 will come through here. Okay, once it comes here, right, the current will split. Okay, you have I2 and then you have I3. So this is also I3. This one is I1. Okay, so I can write aside. I1 equals to I2 plus I3. Okay, then because you can see that these two are parallel to each other. Okay, so I can say that because CD is parallel to FG, right? I can say that VCD is equals to VFG. Okay, and VFG, right, is equals to VR2 plus VB. Okay, so these two paths are in parallel, so they must have the same potential difference. These two, these two will share the same, will split the potential difference accordingly. Okay, then I also can say that VC, okay, I also can write some other stuff like I can write that, oh, VA is equals to VCD, right? So that's what we have. Okay, we can work out current. Okay, we can see that I2, right? I2 is equals to power across A, power dissipated by A, divided by potential difference across A. So this is 0.50 watts over 5.0 volts. So this is 0.10 ampere. I2, right? Okay. I3, I can do the same as well. I3, yeah. I3 is equals to PB over VB. Okay. Okay. How do I know it's correct? Because they say that the lamps are operating at their rated voltage. So this is the rated voltage. Okay, that means they're operating at this correct value. Okay. The lamps, sorry, wait, I take a phone call. Staff room phone also got spam call. Okay, can. Okay, so this one that sub in, this will be 0.50 divided by 2.50, so I get 0.2 ampere. Oh, can. Okay, then okay, I can find VR1. Okay, VR1. VR1, we look at this path here. This path, come back here, must drop by 10 volts. Okay, if this drop is 5 volts already, right? Nothing else here, right? This one must drop by 5 also. So I say VR1 plus VA, right, is equals to 10 volts. So VR1 is equals to 10 minus VA, which is 10 minus 5. I get 5.0 volts. Okay. Uh, okay, so what's the reason for finding this? Okay, then I know that, okay, I want to know I3, I1, right? I1 is equals to R1 over R1. Okay, so if I submit the values, this is 0.1 plus 0.2 equals to 5 over R1. So R1 is 5 over 3, 5 over 0.3. So I get 16.7 ohms. Okay, so that's R1 over here. Okay, then I think it's a bit messy. I should just continue black color on this side. Okay, then I need to find VR2, right? Okay, so I know that VR2 is equals to VFG minus VB, which is 5.0 minus 2.5. This is 2.5 volts. So R2 is equals to VR2 over I3. So this is 2.5 over 0.2. So I get 12.5 ohms. Okay. Okay, a bit long, this question. You probably can try to simplify a bit. And technical break, pause. Yeah. In Interestingly, just now the phone call was a spam call, a UOB spam call, as in like those fake ones. Then the whole staff room, the phones are all ringing. So basically, I think when they call, right, they just iterate the number up by one, they just call. Because the staff room numbers are like my table and next table is probably a difference of one. Just call. Okay, okay, next question. Last time, 1 mark. I thought of this for very long. I cannot solve it. Then I think, and then finally, okay, the trick is, okay, okay, let's talk about it first. Okay, this circuit, EMF of 2.2 volts, 12 volts, inverter resistance of 10 ohms, 7 ohm resistor and R3. State the resistance of R3 such that there's maximum power delivered to, I'm going to highlight this in super red. I'm going to highlight this. Only the R3. Okay, very important. Because okay, the usual circuit we are doing this is like that. Our circuit is usually like this. R, EMF, and then we have external resistor R. Okay. Then we kind of talk about maximum power theorem. So you have max power to R when capital R is equal to small r. Oh, remember this? The small note in the small section that we don't derive, but you expect to know lah. So this is our maximum power theorem. Very important now. Okay. So here, right, my problem was that I look at this guy. I look at this 10 ohm guy. Then my first thought, this one must be 10. Oh, but answer is not. Answer is 17. Then I think very long, right? Then I realized the problem here is that when you talk about this, right? This when you talk about when I came up with the conclusion this is 10, right? This is based on the assumption that there is one internal resistance and one external resistor. So the maximum power, in this case, your terminal voltage is across capital R only. Okay, but in this case here, right? Your terminal voltage is actually across 7 and R3. Okay, so you can't, and then okay, so you want to find the maximum power delivered to the whole circuit, then these two together must give you 10. Okay, so if you treat these two as a single resistor, right? In order for your maximum power delivered to these two resistors, right? The sum of power delivered to these two resistors is maximum, right? These two must equal to 10. But here, right, I only want R3. Okay. So the consideration now becomes that, okay, that means this guy cannot be part of my consideration here. This guy here, right, has to be treated as internal resistance here. Okay. So now I basically, right, my circuit here becomes wider like this. Like that. So that means if I write out, right, my effective internal resistance here, right, becomes 10 plus 7. So this is 17 ohms. Okay, so to have max power across, what am I writing? Okay, so let's write. So I think I write words. So to consider max power by R3, we treat 7 ohms as part of internal resistance. Okay, so now that means my to get max power of R3, R3 must be equals to R, right? So this will be equals to 70 ohms. Okay. Okay, so this one I spent 20 minutes thinking about it. I don't know what the
Sure,
answer
if they
was.
sure if they give like
Huh?
similar question, but then they put it in parallel, then how?
Parallel, as in 7 and R3
R3,
in
yeah.
parallel. Oh, then maximum power across wow, I never thought of that before. Uh I'll add internal resistance and 7 ohm in parallel first. So your circuit looks like this, is it? Your circuit looks basically where I draw. So 12 R, and then it. Like that.
Yep. Yeah.
Yeah, I would treat. Huh. I'll treat these two in parallel first.
Okay.
I think so.
Hmm.
I'm not really sure. I never tried this kind of question before. Uh, yeah, interesting question. Food for thought for later. Okay, can. Tell this one. Okay, this one we set for mid-year or prelim, right? Ideal. Okay, non-ideal one will look like this. Non-ideal will have it's a fatter line. Maybe that and go like that. This is non-ideal. Okay, I think it's a bit too fat. Wait, fat shaming this line. One. This small activation voltage. Maybe one. Okay, so this is non-ideal. Ideal, straight line. Wait, sorry. Straight line. That. Okay. Damn it. Straight line. Yeah, there, right? Then straight up. Like that. Okay. There's no need to have a little bit of potential difference to trigger it. Okay, just go straight up. Okay. Next one I wasn't planning to go through. 5 minutes. Last question already. How much time have we spent? 1 hour, right? Anyone needs 5? I never do 5. No one needs, Then you go shopping. Need just type. Don't have, Last call. Okay, can. Then we prepare the course. Okay, so my consult slots are still available. Please go and book. If you want Zoom, it's okay. And you want face to face. Face to face, I prefer in the morning. If not, you let me know. We can always work out arrangement. There are slots on the weekends as well. The only time I kept free for myself is like Friday afternoon onwards, and then Saturday and Sunday afternoon onwards. Okay, so but I think you let me know, see whether it works also. If you can't find any slots, then let me know. Because I think next week once your A's start, right, it's going to be hard for you to find slots that you are free and I'm free also. Okay, so try to book stuff this week if you can lah. Okay, if you want to come with someone, I think 2 to 3 persons maximum is okay. Yeah, because if you have more, and then what happens is that usually one person never study, the person is just coming along for the ride, just want to like listen, learn by absorption. It doesn't work. You need to try questions first before you can do anything. Okay, so please go and think about what you want to ask, then come and ask. No, you don't take too much time. Okay, I also want to check something. Hold on, let me confirm when's your last paper. SCAB. Sorry. CAB level calendar. What day do you guys end on? That's now 29. Okay, 29th can. So we will do consult 20, yeah, correct. We'll do consultation 29th lor. So 29th daytime I can still morning if you got questions to ask, I can still handle. Let me just do a quick check that I don't have any paper on 29th November. Yeah, I don't have any. Okay, so you can still ask the 29th November. Just nice I'm applying off for 29th night. Okay? Yep. So I think that's all. So please go and see which wow, you need help, I'll just go and book lah. Okay? Okay, thank you. And go already. Bye.
Bye bye.
Uh,
Bye bye.
bye.